Hello and welcome to the Math 171 online teaching lesson for section 4.1 about exponential functions. It's an introductory lesson on exponential functions. In fact, let me call up the first page of this section in your text, exponential functions and their graphs. And we're going to really start right at the beginning. This is going to involve much work with exponents, obviously. We'll quickly get into, in this unit, we'll quickly get into logarithmic functions also in the very next section, 4.2. And then we're going to be doing applications with these types of functions and solving equations with exponential and logarithmic expressions. And also later on in this unit, we're going to have, wrapping up the 171 course, we're going to have a few sections also in Chapter 8 on solving various different types of systems of equations. So that's a new unit that we're starting out here. This is the fourth unit of Math 171, the very first section here being about exponential functions. First of all, exponential functions are a new type of function in that they are not algebraic. Algebraic functions like polynomial functions and rational functions, the values you get with these, if you plug in, for instance, just rational numbers into these things, you always get either rational numbers out or at least square root radical type expressions like the square root of 2 or something. But with transcendental functions, you can get other types of irrational numbers as the output. Even if the input is a rational number, you can get something that is neither rational nor a radical type number. An example of a number that's a transcendental number that you already know about is pi. The number pi is not only irrational, it's also transcendental. There's no rational number that you can put into any polynomial function or in any rational function for x, and the y output will be pi, as long as you input a rational number. But with the transcendental functions, it's very different. So another type of transcendental function, other than exponential, of course, is the logarithmic functions. The next one we're going to study, and then actually in the next course here at Western Piedmont's Math 172, that's when we get into trigonometric functions, and they are a third major type of transcendental function also. Okay, so exponentials. First of all, simple definition of what we mean by an exponential function. It has a base being some real number that's positive and not equal to 1, and that base is raised to the power of x. So our variable for the first time in these functions is an exponent. The variable itself is the exponent. Now, it's not the variable being raised to a power or taking a square root of the variable. No, the variable itself is the exponent. So basic form of this is f of x equals a to the x, where a is positive and not equal to 1, and x can be any real number from negative infinity to positive infinity. It's got an unlimited domain. And first of all, why is it not equal to 1? Because if it was 1 to the x, we all know 1 to any power is just 1. So that is not an exponential type activity going on there. 1 to any power is 1. That's just a straight line. F of x equals 1 to the x is the same as y equals 1. So horizontal straight line. That's not exponential. Similarly, a cannot be 0 or less than 0. If a is 0, 0 to any power is also just 0. So that'd be a straight line, y equals 0. And if a were negative, you get some real curious type results. For instance, a negative number to a whole number even number, a whole even number like 2 or 4 or 6 becomes positive. But to any other power, it's going to be negative. So you get these kinds of functions that keep flipping back and forth across the x-axis, being discontinuous and all, and we're just not going to get into that. So exponential functions we're going to deal with, and in general, this is the general definition, is where the base is some number more than 0, but not 1. And there's going to be two fundamental kinds of these. There's going to be the kind where the base is a fraction between 0 and 1, like 1/2 or 1/3 or 3/4, or the base is greater than 1, like 2 or 3 or 10 or whatever. So those two we're going to see graph very differently, those two basic types, in just a minute here. Now, because we're allowing x to be the exponent and we're saying that x can be any number, you and I are much more comfortable and much more familiar with exponents being whole numbers, or at best fractions, and occasionally even negative whole numbers. But when you start thinking of the exponents being like irrational numbers, like the square root of 2, or even just pick a number like 1.4. What does it mean, 2 to the 1.4 power? We're used to, well, 2 to the third means 2 times itself 3 times. 2 to the fourth means 2 times itself 4 times. Hey, we can handle that. But 2 times itself 1.4 times? Or worse yet, 2 to the square root of 2 power, which is 2 times itself the square root of 2 times, and that's an irrational number of times. Roughly, as you see on the screen here, roughly 1.414 times, but there's just no way we could really comprehend 2 times itself 1.414 times. But actually, it turns out these are meaningful expressions. Since we're going to allow 2 to the x to be our function, then x can be any number. So we're going to have to come out with a way that 2 to any power is meaningful. And let me come back to this evaluation stuff in just a minute. Looking at the graph, for instance, of y equals 2 to the x can be helpful here. Let me, in this graph here, they've got y equals 2 to the x and y equals 4 to the x. And the 2 to the x is the one that's underneath here to the right of the y-axis. 4 to the x is above it. It's going up faster. It's a larger base being raised to exponential powers. It increases more rapidly. But the 2 to the x, you see, for instance, when x is 1, 2 to the first is 2. So when x is 1, y is 2. When x is 2, we're talking about 2 to the second, that's 4. So you have the point 1, 2, 2, 4. And by the way, when x is 0, 2 to the 0 power is 1. So the y-intercept for this exponential function, and it turns out for every exponential function, which is simply a base to some power, regardless of what the base is, as long as it's a positive number and not equal to 1, then the y-intercept is going to be 0, 1. Even if it is equal to 1, it would be. But they all have the y-intercept 0, 1. That's kind of interesting. But the point is, these graphs are smooth, continuous graphs, class. Smooth, continuous. That's every single x value has a y value. There's not a point on this curve that's missing. So since the x-axis down here is made up, it's a number line actually of all the rational numbers and all the irrational numbers, then regardless whether x is rational or irrational, 2 to that power has an answer, and it's the y-coordinate of the point straight above that particular x value. So 2 to the square root of 2, so the square root of 2 is a little bit more than 1.414. It's going to be right somewhere around in here, so it's sort of right there. 2 to the square root of 2. It's a meaningful number. It's a real number. And this graph perhaps can help us visualize why, regardless what x is, what kind of strange number it is, 2 to that power is an actual real number. And what about when x is negative? What happens? Well, if you have 2, for instance, to the negative 1, if you recall your rules of exponents, 2 to a negative, any base to a negative power is simply 1 over that base to the positive power. Anything with a negative power does not give you a negative number. It simply gives you the reciprocal of the original base to the power being a positive number. So for instance, 2 to the negative 1 is the reciprocal of 2 is 1/2. So 2 to the negative 1 is 1/2 to the 1. And anything to the first power, as I trust you recall, is itself. So 1/2 to the first is 1/2. And you see that here on the graph. When x equals negative 1, for y equals 2 to the x, y equals 1/2. When x equals negative 2, that's 2 to the negative 2, which simply means the negative in the exponent tells us that it's the reciprocal of 2, again 1/2, but now not to the negative power, to the positive 2 power. So 1/2 squared. And if you recall how you raise fractions to powers, it's easier than we first think. For instance, 1/2 to the power of 2, you break the fraction into its numerator and denominator, 1 on the top, 2 on the bottom. So 1/2, the entire fraction to the power of 2, is the numerator to the power of 2 divided by the denominator to the power of 2. So it's 1 squared over 2 squared. So 1/2, the whole fraction squared, is just 1 squared over 2 squared, and 1 to any power is 1, and 2 squared is 4, so 1/2 squared is 1/4. That works with any fraction, by the way. 3/5 squared is just 3 squared over 5 squared, so that's just 9/25. So what happens when these exponential graphs go to the left of the y-axis? They go to the left and they go down forever, less and less steeply forever and ever and ever, never crossing the x-axis and never even getting down to it, but approaching it, getting closer and closer forever and ever as x approaches negative infinity, going to the left. It gets closer and closer down to it. It approaches it, as we say, asymptotically, getting closer and closer but never getting there. And then as you go to the right, so it stays between 0 and 1. To the left of the y-axis, the entire graphs of these exponential functions, when the base is greater than 1, the graph stays between 0 and 1 forever to the left. And then forever to the right, of course, it's above 1. And on the right of the y-axis, it goes up faster and faster and faster, literally forever. There is no vertical asymptote. It just keeps going up faster and faster and faster forever. X approaches infinity to the right, and Y approaches infinity, honestly, class, even faster, much, much faster. But X does go on to infinity, and Y does go on to infinity. And so these graphs have the horizontal asymptote of the x-axis, or as we say, the horizontal asymptote of every basic exponential function, just a base to a power. The horizontal asymptote is the horizontal line, y equals 0. Y equals 0, the x-axis, and no vertical asymptote. Now, what happens if we put a negative in front of the exponent? Interesting thing happens. On this next graph, now we see 2 to the negative x and 4 to the negative x. And they seem to be just doing exactly the opposite thing reflected across the y-axis from the graphs right above, where it was 2 to the x and 4 to the x. And indeed, that is the case. If I maybe make this a little smaller, we can see both of them at the same time on the screen. There we go. Upper one 2 to the x, 4 to the x, lower one 2 to the negative x, 4 to the negative x. And indeed, class, that's exactly what's happening, because 2 to the negative x, as we've been discussing, is actually just 1/2 to the x power, and 4 to the negative x is the reciprocal of 4, 1/4 to the x power. And since the base is less than 1, the graph flips like this. And again, why is that? Actually, this is a throwback to chapter 1 discussion we had a couple months ago. If for any function, if you substitute for the input variable instead of x, you put a negative x. If you recall, with any function whatsoever, if you plug in negative x instead of x, and that's what we're doing here with 2 to the negative x instead of 2 to the x, for instance, then that reflects that function across the y-axis. That's what's happening here. It's a perfect reflection across the y-axis. The 2 to the x and 2 to the negative x. I'd like to show you this using Desmos. And let's graph both of these here together. Y equals 2 to the x, and then y equals 2 to the negative x. And I trust you can see what's happening here is these two graphs truly are mirror images of each other across the y-axis. They're perfectly reflected horizontally across the y-axis. They both have the same horizontal asymptote, y equals 0. They both have the same y-intercept, 0, 1. And they are truly reflected from each other across the y-axis perfectly. Every single point would match up perfectly. So, for instance, on the 2 to the x, you have the point 0, 1, 1, 2, and 2, 4. And on the 2 to the negative x, you have the 0, 1, negative 1, 2, and negative 2, 4. And that pattern continues on and on. And let's talk about some of the aspects of these functions too. So, what your text frequently calls a library of parent functions. We're going to look at this for exponential functions now for both a to the x where a is greater than 1 and a to the negative x where a is greater than 1. In other words, that's actually like a to the x where a is between 0 and 1. It comes out to be the same thing, just as we've been talking. But let's look at these two. First of all, on the left, your graph of a to the x where a is greater than 1. So yes, it comes up from the left forever and ever just above the x-axis and getting steeper and steeper very gradually until it crosses the y-axis at 0, 1, and then it gets steeper and steeper quite rapidly. And so, yes, it has the infinite domain of all real numbers from negative infinity to positive infinity. Notice the range, though, is from 0 to infinity, not including 0, because a to the x, as long as x is a real number, and a is a positive number, or no matter what kind of number it is actually, it can never get down to 0. There is no positive number you can raise to any power x and have it be equal to 0. It's not difficult, it's impossible. You also cannot take any positive number and raise it to any real number power and get a negative number. There's no power 2 to this power will give you negative 1. That's impossible. As long as x is a real number. Now, you introduce complex numbers in there for x, yes, you could get a negative number answer. But we're not doing that in this course. So sticking to real numbers, y is going to stay above 0. So the range is from 0, but not including 0, all the way to positive infinity. Y-intercept 0, 1. Notice fundamental fact. The exponential function with the base greater than 1, that function is increasing everywhere. It's not like a parabola that's increasing on half of it and decreasing on half of it. It's increasing everywhere, every interval. From negative infinity all the way to positive infinity, the graph of the function is always moving upwards to the right. Not at the same rate, no, never at the same rate. It's not a constant function. But it is always increasing, and of course, yes, obviously it's exponentially increasing, but it is increasing. has the horizontal asymptote of the x-axis, that is y equals 0. And going to the left, a to the x approaches 0 as x approaches negative infinity. And yes, the graph is perfectly continuous. What about the other one? A to the negative x, where a is greater than 1. That's like 2 to the negative x, or 4 to the negative x, or 10 to the negative x. It's also the 2, 4, and 10 to the negative x are exactly the same as the graphs of 1/2 to the x, 1/4 to the x, and 1/10 to the x, respectively. Same. In fact, if you graph both of them, you'll see it's exactly the same graph. But what's going on here? Well, once again, they have an infinite domain, unlimited, from negative infinity to positive infinity, all real numbers. But the range is from 0 to infinity, once again, not including 0. So it has exactly the same domain, exactly the same range, but it is now decreasing everywhere. When the base was greater than 1, the function is increasing everywhere. When the base is less than 1, between 0 and 1, you have, or if you take the base to a negative power, then it is decreasing everywhere. You still have the x-axis, y equals 0 is the horizontal asymptote, and the function is still continuous and smooth everywhere. No holes, no vertical asymptotes. But now, over here on the first one, a to the x approaches 0 as x approaches negative infinity. Now a to the negative x approaches 0 as x approaches positive infinity. So going to the right, the graph comes down less and less and less steeply forever and ever and ever, approaching the x-axis, never gets to it, never crosses it, but it approaches it. So y approaches 0 as x approaches positive infinity. Let's back up and talk about a couple basic things here. Basic stuff, really basic stuff. Like, how do you use your calculator to do exponents? And I'm guessing probably everybody's pretty efficient at this, but this example 1 is a good one you can come back to if you need some review. For instance, if you're trying to figure out how much f of x equals 2 to the x is for x equals negative 3.1. Well, what does that mean? It's actually like down here, part A. That means you're trying to evaluate how much is 2 to the negative 3.1. Well, with this exponent key, typically if you're using a TI-83 or 84, you've got this exponent key that looks like this caret mark right here. If you're using a different kind of calculator, you may have a different kind of exponent key. So make sure you know how to do it with your own calculator. And of course, then you go to exponent key negative with the negative that's in parentheses to start the expression. And then 3.1, hit enter. And you get 0.1166291, whatever. Well, that's the answer. So 2 to the negative 3.1 is just a little more than 1/10. Because that's actually 1/2 to the 3.1 power. And then 2 to the negative pi is 2 exponent key negative pi, hit enter. And for most of us with a TI-83 or 84, to get pi, remember, you hit the second key and then the key that has pi right above it. I think it's the exponent key, actually. And continuing on, here's one you have to be careful on, this last one, part D. If you're trying to figure out how much 1.5 is to the 2 times 12, if you really want to leave it as 2 times 12, then you got to put parentheses around the multiplication. Not like they have it here, 2 times parentheses 12. You have to do it like over here, parentheses around the entire multiplication, before the 2 and after the 12. And why do you have to do that? Well, if you do 1.05 exponent key and then just do no parentheses and do 1.5 exponent key 2 times 12, here's what most calculators are going to do, not what you want it to do. It's going to do 1.05 to the 2 power, or square 1.05, and then multiply that times 12. And that's not what you want. You want it to be just simply the base 1.05 to the power of 2 times 12. So you have to put parentheses around that, or your calculator will probably give you an unintended result. So what I like to do, and I'm going to suggest this for everybody, is avoid exponents with numbers multiplied like that when you can. Just go ahead and multiply the 2 times 12, get 24. And just figure 1.05 to the 24 power. And that's a lot safer, simpler, less room for unintended errors. Just multiply the numbers in the exponent together if you can, and then get your answer. Now, I'm going to move on to the natural base E. The natural base E. This bears a little bit of discussion here, because to call an irrational number natural, that's kind of unnatural for most of us, I would suggest. Why would we possibly consider an irrational number like 2.718 forever, never, never, no pattern in the decimals, never repeats, cannot express E as a fraction? It's impossible. It's not difficult. It's not a fraction. It's not a rational number. It's irrational. Why would we possibly call such a number natural? And to try to give you just a little bit of a feel for this, this is a number that shows up, honestly, class, in the real world around us as mathematicians, scientists, physicists. As they study the world around us, this number just keeps popping up. It is a number that's built into the very fabric of the universe. We live in a very mathematical universe. The number E just keeps showing up in so many ways. One of the simplest ways to arrive at E is this way right here, right down here at the bottom of the screen, where it says the expression 1 plus 1 over x, all to the x power. If you will enter that in your calculator and graph y equals 1 plus 1 over x, put the parentheses, and then raise it to the x power, you'll notice something. It doesn't just keep getting bigger and bigger and bigger without limit. Very quickly, it approaches about 2.7 and then starts leveling off. It doesn't ever perfectly level off, but it goes off to the right forever as x approaches positive infinity. It just asymptotically goes up to a horizontal upper bound asymptote, which is y equals E. So the very simple expression 1 plus 1 over x to the x power, as x goes off to the right, y goes up approaching the limit or the boundary of exactly the irrational number E. So both in rather simple mathematical applications and in the universe around us in scientific applications, the number E just literally just keeps showing up. It keeps showing up, as the expression goes, in nature. So it's called the natural base E. Now, we can create an exponential function with the base E. F of x equals e to the x. And this is then called the natural exponential function, simply because it has base E. It's called the natural exponential function. Like all exponential functions whose base is greater than 1, and of course 2.718, etc., is more than 1, it starts from the lower left and goes up to the right. Has the horizontal asymptote, y equals 0, has the y-intercept of 0, 1. When x equals 1, y equals e, because y is e to the x, and anything to the first power is itself, so e to the 1 is just e. So it behaves like any other exponential function with a base greater than 1. And down here below you see a graph illustrating what we were just talking about. If you graph 1 plus 1 over x in parentheses to the x power, that's this lower curved graph that's going up to the right and leveling off, forever approaching this horizontal line here, which is y equals e. And with your calculator, you must know how to access the number E on your calculator. If you're using most TI 83s and 84s they all have the number E built into them. But to access the number E, if you look to the right on your calculator, for instance on mine, it's in blue and it's just above the divided key on the right side. On the right side, you have the operating keys, plus, minus, times, divided by, and it's just above the divided by key in the color, indicating that you must first press the second button and then press the divided key, and that will access the number E. So you hit second, divided by, and E pops up on the screen. And then you can hit the exponent key and anything you want, and thereby you can raise E to any power you wish. So, for instance, if you're wishing to raise E to the -2 power, you'd hit second, divided by, get the E on the screen, exponent key, and -2, hit enter, and you get, like they're showing here, 0.13533, etc., etc. Or whatever it might be. If you have to raise E to the 2/3, oh yes, this is a good example here, E to the 2/3. 2/3 is one of those rather simple fractions which gives us an infinite decimal extension. 2 divided by 3 is 0.666666666 forever and ever and ever and ever sixes. You cannot just divide 2 by 3 and put it in there as the exponent. So you really need to leave this as a fraction to be accurate, 2 divided by 3, and since your exponent has an operation embedded within it, it's not times, but it's divided by, the same principle. So 2 divided by 3 is the exponent. That obligates us to surround the exponent with parentheses to get a correct answer. So E to the 2/3, you do E to the power of parentheses 2 divided by 3, close parentheses, enter. And E to the 2/3, since 2/3 is less than 1, it's going to be less than E. E to the first is E. E to the 2/3 is 2/3 less than 1, so E to the 2/3 is going to be less than E, and sure enough, it's 1.947 something something. So now let's spend a few minutes talking about applications of such. Applications of exponential functions. I'm imagining quite a few of you have probably done compound interest problems in some previous math course, situation where money is deposited earning interest at regular intervals, and the interest is then credited to the account and actually credited into the account to increase the account balance, and thereafter the account holder is earning interest on the new amount, the original amount they had in there, plus the interest credited. So they're earning interest on their interest. That's why we call it compounded interest, earning interest on the interest. Benjamin Franklin put it this way: money makes money, and the money that money makes more money. So that's the way he had it for saying compound interest. So I am not going to go through the derivation of the compound interest formula, but I want you to know how to use these two formulas. I'm going to actually give you two formulas now for compound interest. One for the general situations, like a bank, for instance, would credit your interest to your account, or as we say, compound it, once a year or perhaps once a month. That would be 12 times per year, or maybe every 3 months. That would be what we call quarterly, because quarterly compounding means 4 times a year, every quarter of a year, which is a fourth of a year, which is 3 months. Or it could be semi-annually, which means every half year. That would be 2 times per year. Okay. That's your typical compounding situation in the real world, like where a bank or such is paying interest on money that's been deposited. The other formula is a mathematical formula that's not going to actually apply to any bank, unfortunately. They will never give you this continuous compounding. As you see here, the second formula down at the bottom of the page here. Continuous compounding actually means, class, it's compounded every instant. It is also known as instantaneous compounding. So every single instant, the money, the interest is calculated and added to the account, calculated, added to the account, calculated, added to the account every instant. And here you go. The mathematicians figured out some years back, if you have this continuous compounding, then the compound interest formula simplifies down to actually an easier formula, and look what number is the base of the exponent in this formula. It's our number e. So actually this is an example of the number e just showing up sort of unexpectedly. But let's take each of these now separately. The first one is the most commonly used. Now you're going to have homework where you're using both of these, but the first one is for so many compoundings per year, even if it's just one. But here's how it works. If you have a certain finite number of compoundings per year, say n, we're going to call the number of compoundings per year little n. And that shows up actually in this first formula 2 times. The formula, let me say it out loud. A equals P times parentheses 1 plus R over N, close the parentheses, to the power of N times T. When it says NT, that means little n times T. So we have 4 different variables in here other than the A. And we have to know what all 4 of these mean and how to plug them in the formula. So let's start with each one, and actually we start with the A. The A just tells you that's the account balance in the future after the interest has been compounded so many times and the account has grown and compounded. A is how much money you're going to have in the bank at the end of the investment term, after so many years go by, whatever, months, years, whatever. And then the 4 variables you need to plug in to find out how much A is going to be, first of all, is P. P stands for principal. Spelled the same way as the principal of a school, but this is principal being an amount of money that has been deposited and it's earning interest. It's just a technical legal term for money upon which interest is being earned. It's called principal. So for instance, if the principal was $10,000, you'd have 10,000 in here for the letter P. Then times parentheses 1, that's fixed, plus little r over little n. Well, little r is the interest rate, and actually it's the annual interest rate, and it must be expressed as a pure decimal. It cannot be left as a percent number. If you leave it as a percent number, you will get a terribly wrong answer. So for instance, little r, if the interest rate was 4%, little r then would not be 4, it would be 0.04. 4% converted to a pure decimal. Remember, you take a percent number, move the decimal point 2 places to the left, and you get the decimal form of the percent number. If little r, if the interest rate, the annual interest rate was 6.5%, well, 6.5 is 6.5%. And then you would take the 6.5, move the decimal point 2 places to the left, it would be 0.065. That would be little r. Then you would take the little r number and divide it by the n number, which is simply the number of compoundings per year. It is the number of times the bank is crediting interest to your account. So if they're crediting it, for instance, every month, little n equals 12, because the interest is being credited and your account's being compounded 12 times per year. So n would be 12. If they were doing it quarterly, n would equal 4 times a year, every 3 months. If they were doing it semi-annually, N would be 2 times a year. 6 months, there's 2 6-month periods in a year. If they were crediting your interest just once a year, just annually, then N equals 1. And you must notice, little n is the only variable that shows up in the compound interest formula 2 times in 2 different places. First of all, it's a denominator in the fraction r over n inside the parentheses. You divide the little r by the n. Then secondly, in the exponent, n shows up here. It's going to be the number of compoundings per year, n times t, which is the number of years. So t is always a number of years, n is always a number of compoundings per year. So let's consider that. If you left some money in there, say for 5 years, and it was compounded monthly, the interest was, well then, compounded monthly, that means little n equals 12, and when it's being left for 5 years, so t equals 5. So your exponent then being n times t, the exponent is going to be 12 times 5, and I recommend going ahead and multiplying that out, and you get 60. So instead of leaving the exponent as n times t, 12 times 5, and you have to put it in parentheses with your calculator, no, just multiply 12 times 5, get 60, and then all you have to do is raise that parentheses to the single number power of 60. So that's how it works. N times t is the exponent. And let's do an example with this, and then we'll come back to this second formula here for continuous compounding. So, example 8 in your text, finding the balance for compound interest. So a pretty straightforward example right here. $9,000 is going to be invested. That's the principal amount at an annual interest rate of 2.5%. We're going to get our little r from that number. And it's compounded annually. Find the balance in the account after 5 years. So we have to figure out how much P, R, N, and T are. Well, P, the principal, is straightforward. It's 9,000. Little r is 2.5%, which then as a pure decimal, moving the decimal point 2 places to the left, becomes 0.025. Little n, because it's compounded annually, that is 1 time per year. So the number of compoundings per year, n, is equal to 1. So n equals 1. And we're doing this for 5 years. So t equals 5. So plugging all those numbers in our formula, a equals p times 1 plus r over n to the nt power. A is going to then equal 9,000 times parentheses 1 plus 0.025 divided by 1. That's nice, doesn't change it. Close of parentheses to the power of 1 times 5, but that's, let's do that. 1 times 5 is just 5. And 0.025 over 1 is just 0.025. And 1 plus 0.025 is simply, as they show you here, 1.025. So this one's nice. It simplifies down very nicely. They all don't do that. For instance, if you have n equals 12 and your top number is something that's not divisible by 3, the interest rate little r, then when you divide it by 12, you actually get a decimal number that goes on forever. And so you don't want to take little r over little n, divide it out, and then round it off and add it to 1, because when you round that off and then you raise it to some big power, most of your powers are going to be more than 5. It's not unusual to be raising it to the 60th or 120th or even 360th power, and you're simply then going to compound your error where you rounded that off. You're going to compound it 120 or 180 or 360 times, and your answer will be way off because of that. It will be wrong. So in this case, 0.025 over 1 is nice. It's just 0.025. Add that to 1. So 9,000 times 1.025 to the fifth. Now, of course, it's only the 1.025 to the fifth power, not the 9,000. So 1.025 to the fifth, and then times 9,000. Here's the answer to the nearest penny. Always round it off to the nearest cent, nearest hundredth of a dollar. The answer then is $10,182.67. That is the total balance in the account after 5 years. Now, just to clarify, that is not how much interest will be earned over the 5 years, because the account started with $9,000 of the investor's money being put in the account, and it went from $9,000 up to $10,182 something. So it increased by a little over $1,182. That's the amount of interest. So honestly, just to figure the amount of interest, all you have to do is take that ending balance amount and subtract the original amount that was invested or deposited, and the difference then is the interest that was earned. But just the point that that capital A amount that the formula outputs to us is not the interest earned, it's the total account balance, including the original deposit plus the interest earned. Okay. What about with continuous compounding? Let's go back and look at that formula. Continuous compounding. Yeah, simpler formula, but it's got that number that many people are not so comfortable with, that little irrational number E. So here you go. If you actually have a situation where something is compounded instantaneously, then the formula simplifies to this. The future account balance, capital A, is equal to the original principal amount deposited, that's capital P, times just e to the RT power. So the principal amount times e to the exponential power of r times t. And r and t are the same as in the previous formula. So little r in the exponent this time is the annual interest rate in pure decimal form. So again, if the interest rate is 3% per year, 3% as a pure decimal will be 0.03. And t still is the number of years. So if you have it in there for, say, 6 years, and it's at 3%, then you have A equals P times e to the 0.03 times 6, and go ahead and multiply those out, keep it simpler, don't have to use parentheses around the exponent. So A equals P times e to the 0.18, 0.03 times 6 being 0.18, it'd be the principal amount times e to the 0.18, and that's actually how easily you get your answer then. So for instance, an example, if $12,000 is invested at an annual interest rate of, here we go, 3%, find the balance after 4 years with quarterly compounding and then continuous compounding. Well, quarterly is going to be n equals 4, and you'd use the other compound interest formula as we just practiced, and you can follow along there and look back at that later yourself if you like. But I want to jump to the continuous part. Principal is $12,000, annual interest rate 3%. After 4 years of continuous compounding, what's the account balance going to be? Well, formula is A equals P times e to the RT. $12,000 is invested, so P is 12,000. Little r and little t, annual interest rate of 3%, that's a pure decimal, gives us 0.03. Number of years, t is 4. 0.03 times 4 is 0.12. So it's actually then capital A, P times e to the RT is 12,000 times e to the 0.12, e to the 0.12 power. And that gives us then the answer rounded to the nearest penny. Again, the decimals you get will go on and on and on for a while. But rounded to the nearest penny, it is $13,529.96. And just a quick pointer here. if we had followed through the previous example in detail with quarterly compounding, same amount of money, same interest rate, still for 4 years, it would have come out to just $13,523.91, and with continuous instantaneous compounding, it gave us $6.05 more after 4 years. Not a lot of money more, but you notice it is more because it was compounded obviously more frequently. And so this is the limit of how much money you can make at any given interest rate for any given amount of time. The most you can make is with continuous compounding, and that is that's the limit of what you can make. So even if you have instantaneous compounding, it's not going to turn you into a millionaire. There's a limit to this. One more example type I'd like to go over with everybody here in this introductory lesson on exponential functions, and that is using exponential functions to do calculations with radioactive decay situations. Radioactive decay is what occurs with radioactive isotopes of various elements, where the isotopes, the atomic nuclei, actually spontaneously decay, as we say. They give off some kind of radiation and become another isotope or another element, typically, as a result of this. It just happens spontaneously, naturally, and scientists have studied this, and they've determined that these things happen at a predictable rate. So if you started, for instance, with 8 pounds of some radioactive substance, they can say, well, after so many years, you'd only have half that left. You only have 4 pounds left. And after so many years, the 4 pounds, only half of that would be left, and you'd only have 2 pounds, for instance. They found they do decay at predictable rates. And the term they've come up with to express this is half-life. You may have heard this term. The half-life of any radioactive element is that amount of time, which for that particular element, it's the amount of time required for that amount, for any amount of that element, to reduce down to 1/2 of what it was originally. That's the half-life period. So if it takes, for instance, 10 years to reduce down to half what it was, we would say the half-life of that particular element was 10 years. Now, some are just a few years, some are many, many years. Some are actually, there's some half-lives that are only in minutes or seconds, or even very small fractions of a second. There's some radioactive elements they make in the laboratory, for instance, with various reactions, and they only last for a very tiny fraction of a second, and they radioactively decay. They're gone. But let's look at an example of one which has a half-life of, in this case, 29 years. Strontium-90. And here's how you do a half-life problem, class. We're going to use 1/2 as the base of the exponential function. And the formula for half-life is that the amount that's going to be left after a certain number of half-lives is the original amount that was present times 1/2 to the power of the total amount of time divided by the half-life. Now, it's actually, you can just say it's the original amount times 1/2 to the exponent being the number of half-lives. That's a simpler way to say it. And in this particular case, half-life is 29 years, and the formula for the amount present after t years is 10 times 1/2 to the exponent of t divided by 29. So notice t is the number of years, 29 is the half-life. So for instance, if t was 29 years, then 29 divided by 29 is 1. So that'd be 1/2 to the 1 power, which is just 1/2. And 10 times a half is half of 10, that's 5. So since 29 is the half-life, after 29 years, plugging in 29 for t, then you have 10 times 1/2 to the first. You end up with 5 pounds or grams or whatever it is left. I guess they're talking about grams. In fact, that number in front of the 1/2 in the parentheses, the number 10, actually indicates how much of the stuff is present at the beginning when t equals 0, the initial mass, as we say. So whenever you're given a formula like this, if you plug in 0 for t, then you can find out what's called the initial mass, the amount at the beginning of the time period. So let t equal 0, and of course 0 divided by anything is 0. So you're raising the 1/2 to the 0 power, and anything to the 0 power is 1. And so then it becomes 10 times 1/2 to the 0, 10 times 1, so anything times 1 is itself. So the initial mass then when t equals 0 is 10. So whatever the number is in the equation, in the coefficient of the 1/2 to a power, that coefficient number is going to be the initial amount present at t equals 0. And how much would there be after 80 years? Well, that's not an even number of half-lives. You can't divide 80 by 29 and get a whole number, no. So you just have to leave 80 over 29 as the exponent. And of course, with your calculator, you'd have to wrap that in parentheses, and you'd say y. Y stands for the amount left after t years. So y equals 10 times 1/2 to the 80 over 29, which is roughly 2.759. Anyway, that comes out to about 1.48 grams. So having started with 10 grams with a half-life of 29 years, it goes away by half every 29 years. After 80 years, you're down to a little less than 1.5 grams. So that's how the half-life formula works. I do want to point out one more useful thing in this section here. It is actually at the, I think it's this page. Yeah, down at the bottom of page 325 in section 4.1, it's a nice little summary review of the rules of exponents. I wanted to point this out to you before we bring this lesson to an end. The way all these basic rules of exponents work, I trust you've seen all these before, but it may have been a while. This is a nice place to refer back to these, that a to the x times a to the y is a to the x plus y. So if you have a base to a power times that same base to another power, it equals that base to the power being the sum of those two exponents. You just add the exponents. When you're multiplying, you add the exponents. Just oppositely, if you divide, you subtract exponents. So a to the x divided by the same number a to the y power is a to the x minus y. And as we talked about a while ago, any number a to the negative x power is just 1 over a to the positive x, which incidentally is also equal to, since 1 to any power is the same, it's just 1 over a to the x power. Anything to the 0 power is 1, even x. Even the unknown number x to the 0 is also 1. A product to a power, the number a times the number b, in parentheses, all that raised to the x power is exactly equal to a to the x power times b to the x power. A to the x power itself raised then to the y power, a to the x, all that to the y power is simply equal to a to the product, to the exponent being the product of x and y. So a to the x to the y power is a to the x times y. And if you have a fraction to a power, this is very useful actually. A over b to the x power is simply a to the x over b to the x. The fraction to a power is simply equal to the numerator to the power divided by the denominator to the power. That's nice. That helps a lot. The last one is pretty simple, that the absolute value of any number squared is simply equal to that number squared. Pretty straightforward there. So a good, nice summary of the rules of exponents here available to you at the bottom, page 325 in your text. And that concludes our lesson on section 4.1 about exponential functions and their graphs. So I hope this is helpful, and do wish everybody a good day here. Thank you there. Bye-bye.